So I'll first go through this week's content and then we'll do some practice questions. Um, Most of this deep learning models that we will be discussing, they follow a general template, and this template is what is called as a learning paradigm. And if we understand this template, then you will notice that every new model you encounter, uh, they simply fills the same slot with different pieces. So whether it is linear regression or logistic regression or a deep neural network, they all follow a similar pattern. So first in this week's video, in week 4 video, uh, actually, this is week 5, I think. So, in the last, the assignment had to be submitted on Wednesday. So, the last week video, mainly the linear regression is introduced. And if you understand this template that is discussed in linear regression, then you will understand neural networks easily. So, the video starts with discussing classic, like the traditional programming versus machine learning. So in classical programming, we usually write down the rules and then we give the computer some data and tell it exactly what to do with the data. You give a set of predefined rules to the computer. And outcome is the answer that we want. If we take as an example, suppose I want to write a program that convert the Celsius to Fahrenheit scale. We use a formula. We already have this predefined formula. So this is the rule, and the programmer already knows it. So we write the rule and we write the program. But machine learning, it works in the opposite direction. So you give the machine raw input data and the corresponding answers to it. And the machine is expected to find out what are the rules. So this whatever finally comes as the rules, that is the model. So a model is essentially any mathematical function that takes in some input and produces an output. So this is the difference. I think all of you know that the difference between classical programming, where you already know the rules, but when it comes to machine learning, you don't know the rules, but you learn the rules through the data and the answers that we already know. Now coming to another definition. So in machine learning, the word model and this hypothesis function, they are used interchangeably. So we say this function it could be this function it could be a linear function, a quadratic function, an exponential, anything it could be. It can take, if it is a linear function, it can take the form. Linear will be something that is expressed with a line. So it can take this format y is equal to mx plus b when it takes a linear function. And the how do you choose whether you want a linear function or whether you want a quadratic function or a cubic function is based on your knowledge of the problem. So initially we try with different things and see what it works. Also, if you know a lot about the problem, if you have a knowledge about the domain, then that can also help you find what will fit your data. So, so there are these things. So this you can also write as W0 plus W1x. So instead of M and A, you replace the M and the B by W0 plus W1x. But in ML also, as far as I understand, hypothesis function is given as, yeah. So that is what that's what I said in the beginning. This model and hypothesis function is something that is used interchangeably. Uh, you decide initially itself that you want to use a neural network, or you decide in the beginning itself that you want to use linear regression because your data is a regression task. So it is something that is known already, or you should have some domain knowledge about it already. Yeah, so y is equal to w1, w0 plus w1x. You can rewrite this as this. So same expression for a line. So these are this. So for this function, this w0 and w1, these are called as parameters, or it is also called as weights. And these are not known in the beginning. You start with some random initial values, and then gradually your model or the machine learning algorithm will learn this parameter such that it is optimized for a certain level of accuracy or a certain level of error in your data. Okay, so suppose you have an input vector x, and this x has two components x1 and x2, and you write the hypothesis function h of x w is equal to w0 plus w1 x1 plus w2 x2 plus w3 x1 x2. So here this includes this includes one this constant term, one uh, like two linear terms. So constant term is this one, which is taking a value w0 into 1. So usually we say it as x0 and it is always 1. That is the constant term. And this one, these are the linear terms. And this is something that is called as an interaction term. So this four are the unknown terms that this W0, W1, W2, W3, these are not known initially, but the learning algorithm or the model will find it. Um, so that is how this works. Now, then in the video, they have described about ground truth and prediction. So ground truth is what actually is correct about the data, the correct answer to the data, and or it can be something like the house price. For example, in case of predicting your house price, you will be already knowing the price of the house. So that is ground truth. Or for example, a doctor's diagnosis on something. That is something that you already know. And prediction is it is what our model outputs. So this is what the model will output when given a certain input. So this is usually denoted as y hat, and this is usually denoted as y and y hat. So the goal of machine learning algorithm is to make this prediction y hat as close to the actual answer. That is the main goal of learning. Then another term that is introduced is the cost function. So you so here we told that the learning algorithm will find these parameters W0, W1, W2, W3, etc. Now you have to determine whether the weights, the set of weights that we have estimated from the algorithm, are they good or bad? So we need a single number that will tell us about the discrepancy between our y, which is the ground truth, and our prediction from the model, which is y hat. So this number is called as the cost function. So this is what we call as the cost function. Uh, and when the y hat equals y for every example, then the cost function j will become 0. That is, the model is like a, if it is a line uh, that we are using as the hypothesis function, then the line is a perfect fit for that data. That is what it means. But larger the gap between the predictions and the ground truth, then this j will also become larger. So here learning is mainly, then it is becoming an optimization function. So not optimization function. Learning is mainly becoming an optimization problem. So you are trying to reduce the discrepancy between the ground truth and the prediction. And then, so that is how you determine that your weights are good or bad. So then it becomes an optimization problem. That is, find the weights that minimize your cost function. So then about cost function, there are many types of cost function. What you want to choose depends on the type of problem that you are dealing with. So for regression problem, mostly the cost function that is used is the one popular choice is mean squared error. For classification, cross entropy is one popular function that is used as cost function. So we will learn this as we like come across videos of different applications. Now, the learning the universal template. So first, how we start with is we have a input data, which is x, and you have a function f of x that is going to transform your input to your output y. and the prediction that the model makes is y hat. So this f of x, it is a function of some weights and input. So these are matrices. It's I just so the large capital letters always mean some metrics. So you have the data and W is the weights. Um, so you have to find a set of W or the set of weights that reduces the discrepancy between your prediction and your actual input. And in this, to do this, we first take the input and then guess some weights W, and then we pass them through this hypothesis function, the f of x. It could be W into x or it could be anything depending on the model or the algorithm that we are dealing with. So there is some function f of x, we pass through it, and then we get a set of prediction that is called as the forward pass. It is also called as the feed forward step. So nothing is, so in this feed forward path, there is no learning. It's just calculation of the weights into the input, or depending on the function, depending on the f of x, whatever calculation is there, that is done in the forward pass. Then after the forward pass, the cost is computed. The cost function is computed. That is, you compare y hat, the predictions, against the actual, the ground truth y. And this is done with the cost function j. Depending on the problem, we select a cost function. And if this j is 0, then we found a perfect fit. If not, we need to improve the weights. So it's not just, as we have mentioned in the last class, it's not just one possibility that j is equal to 0. There could be another set of stopping criterion as well, as we discussed in the last class. So this is one criteria where you want to reduce the discrepancy between y hat and y. So j becomes 0 is one case where we got a perfect fit. And if that happens, then okay. Otherwise, we go back and correct it. What we need to correct? We need to correct the weights. Now that is the feedback path. So you have the cost function. You want to find the direction along which you should move such that your cost function is reduced. So for that, we can use what? We can compute the gradient, and then you update the gradient of this cost function j with respect to each of the weights w. So the gradient will tell you the direction in which the cost function is. I mean, the negative of the gradient will tell you the direction in which the cost function is going to the minimum value. Now, based on that, you update the weights. So this is the gradient descent. We have discussed it in the last class. We take the gradient and then we update the weights. And then this is the learning rate, which is the step size. And we also discussed the consequences of different values of learning rate. So we've got a new W value. Now what we do is we go to the first step here and then again give the input x and then do this calculation f of x. It could be w into x, and then again calculate the prediction, which is y hat. Then this process again, so that is the next forward pass. Again, you compute the cost, compare y hat against y, compute the cost. If the cost is 0, then fine. Otherwise, you again go back and update the weights. So, this is the main uh, process that happens inside the learning paradigm, the main template with all these algorithms. Now, see, one thing is that the algorithm cannot figure out everything by itself. We have to give many inputs for the algorithm to work. So, first there should be a proper data set that can give us the answers to our problem. Second is that we need the good data, and also another thing is what function to use, the f of x, what model will fit our data well, that is another thing. Then choosing a good cost function, what cost function will tell us correctly whether we have got a good function that map our input to output. And also another factor is the optimization, the way you optimize the function. So here we have, last class we discussed about a simple gradient descent, but it could be, so there are many different variations of it. So what optimization can help our data learn, I mean our algorithm learn the mapping well. So these are uh, the main factors: the data, the model, the cost function, the optimization method. These are all main things. Then in the lecture, they start discussing about linear regression. So, regression, as we all know, is the task of predicting a continuous output given some input data. For example, predicting stock prices. So, it is one of the two fundamental type of supervised learning. Other is classification. So in regression, we will have a set of data points with known inputs and outputs, and we want to fit a model that can predict the output for any new input that is not in the original data set. So in the video, they show an example with the temperature, this thermal expansion coefficient of steel. So they show a table of measurements at various temperature, uh, and they want to predict the coefficient at a certain temperature value. And so in the video, sir talks about one easy way is to linearly interpolate the data. Uh, so that is one easy way, but it we have, so as you might have seen in the video, there are a lot of rows, and the temperature, the expansion coefficient at 70 degrees is asked. So there is 60 and 80 you can interpolate, but then still the other in, like, there are many other information also that we can make use of. So interpolation, if we use it, ignores most of the data. A better approach is to use all the data to fit a model. So you can use all the data to fit a model, a curve that captures the overall trend, and then there are already built-in functions like linear fit, quadratic fit, cubic fit, etc., that you can use to fit a curve on the data. But then, as you see in the video, that linear fit captures the trend, but there is a lot of error. And then quadratic fit is better than linear fit, and cubic is even better. Um, so then, one question that arises is that how do we formally decide which model is best? So then the question is, how do we decide which model is best? So this you will like we will come to this answer soon when when we talk about different evaluation metric and also the bias variance trade-off. The linear fit is there, uh, quadratic fit is there, and this cubic fit. So for each of these three fit, there are three different functions. So when we take linear fit, this is just W0 plus W1x. And then when it is quadratic fit, it is W0 plus W1x plus W2x square. And then cubic fit, it will have x cube term in it. So the this is something that we have chosen, and also the weights W0, W1 in linear and also in quadratic, we need to determine these values. And if like in MATLAB and Python and all, there are already existing curve fitting function. They use some analytical solution to find what is the value of W0, W1, etc. So we will also, like in linear regression, you can also derive this analytically. What should be the value of this W? Um, and also, that is so there are two ways in which we can derive the values of this W. One is an analytical solution for linear regression, and another one is you can iteratively find the solution using algorithms like gradient descent. Okay, now coming to this analytical solution part. So we have our hypothesis function y hat, which is equal to W0 plus W1x. And this is for, if I take each row in the data set, which is a sample. So this is my sample or data point I, each row. And the ground truth is yi. The difference between them is yi minus y hat I. So this is the prediction error for that point, yi minus yi hat. This is the prediction error for that point, and we want for all the different data points, this prediction error must be a minimum value, or it should be small. So natural way is to square them and make them, add them all up and then divide by the number of samples. And also another way is like for mathematical convenience, they usually add a half in front of it, and finally we call it as mean squared error. Uh, like 1 by, if I have n samples, sigma yi minus y hat, the whole square, which is over n. I is from 1 to n. So this is what we want to reduce. So this is the cos function, the mean squared error, and this is the function of weights. Different values of w will give different values of this cos function. So we want to find the w that makes this cos function as small as possible. Ideally, it should be 0. Though in practice, it is something that can be rarely achieved. But then ideally, it should be a very small number. So then we fit uh, this curve fitting to we make this fitting problem to an optimization problem. So we find the best fit into a minimizing a function. Um, so how do we uh, do this is the gradient descent algorithm. It tells us that we start at a certain initial value of w, and then we compute the gradient of j with respect to w, and then we update the weights of w and take a like it will allow us to go downhill and reach the flat bottom where the gradient is 0 or null or it is stable. So to apply this gradient descent, we need explicit formula for the partial derivative. We have discussed this in the last class. Um, so as they tell in the video, so they take the derivative of this cos function with respect to each of the weights w0, w1, etc. up to w n. How many ever weights we have, we take that, and then uh, this function derivative is taken with respect to uh, w. So that is y hat is w0 plus w1 x I. So, for example, in one case, when we take the derivative of cos function with respect to w0, you get minus 1 by n sigma I yi minus y I hat. That is, so here there is only one w0 term. So we are taking the derivative with respect to w0, and that is 1. And yi hat is, you can replace it by w0 minus w1 xi. And you get minus 1 by w sigma yi minus y hat. So this is just the mean. So this is just a negative mean of the errors across all the sample. So if the model is consistently predicting too low, all the errors will become positive and this gradient will be negative, and the W0 will push W0 upward, and that is what we want actually. And similarly, you can apply this derivative of the cos function j with respect to the other weights as well, W1, W2, etc. up to Wn or Wr. So this is explained in the video, and once we have the gradients, then the updates rules are straightforward. You just update w is equal to w minus alpha times the gradient of j with respect to w. And this alpha value is something that you already choose before training. If alpha is too large, then it will oscillate a lot. And if alpha is too small, then convergence will be very slow. So finding a good alpha is also a difficult uh, or a skill or an art in machine learning. So then coming to stopping criteria, last class also we discussed if the cost function has not changed a lot, then I mean this cost function of the current iteration minus the cost function of the last iteration. If it is a very that difference, if it is a very small value, then the cost function has not changed a lot. So we stop the weight updation at that point. The second one checks whether the weights have stopped changing. That is the W current minus the W, the previous iteration is a very small value. And the third case is when we have a fixed number of iterations, then also once we have passed that many number of iteration, then we will stop. So these are some of the conditions, the stopping criteria conditions. So I will just quickly go through some practice questions from whatever we have discussed. Yeah, so when y hat is y, which is impractical, difficult, but that is when j is equal to 0. Yeah, so it is two parameters. So here the answer is to cancel the 2 from power rule while differentiating. So the mean square error is 1 by 2 yi minus y hat the whole square. And so there's a sigma and n. And so when you differentiate this, there will be 2 times y minus y hat coming. And to cancel this 2, they have added 2 in the uh, power rule. Which stopping criteria checks if the weights have stabilized? Yeah, both of them, right? So W current minus W previous, if the weights have also not changed, if the weights have also stabilized, then that also is a stopping criteria. Then they talk about normalization. So, normalization, the main idea is to transform all the input so that all the inputs are on a similar scale. Um, then it is easier. So, one main advantage with that is for this algorithms that use this gradient descent, they kind of converge smoothly. And there are different ways of doing it. So one is this min max scaling, and it will map any input to a range 0, 1. The maximum will be 1 and the minimum will be 0. And then there are this Z score normalization where you subtract by the mean and then divide by the standardization. Uh, so these are some ways to do normalization. And then another thing that is discussed in the lecture is the something is wrong with the pen. Uh, the goodness of the fit. So the cost function will tell us the mean squared error of our predictions. But if suppose if mean square error is 100, what does it mean? Is it a good fit or is it a bad fit? It depends on what is your y. So what we need is a normalized and also a scale-free measurement that lies between 0 and 1, where 1 is the most fit solution. So we can immediately judge how well our model is doing. And one such metric is this R square metric, and this is given by SSR by SST. So that is R is the sum of squares regression, that is yi minus the y bar. This is that is how much the model's prediction vary from the mean, the data mean. So if it is a good model, it will have a high SSR. It should explain most of the data's variability. And SST is the sum of squares total. This is given by yi minus the whole square. So this will tell how spread out the actual labels are from the average or from the mean. And then this SSE is a sum of squares error, and this is given by yi minus pi hat whole square. So this is R square, which is a fraction of total variance that is explained by the model. It's also called as coefficient of determination. So if we have a higher value of R square, that means the model is perfect. That is, if R square is 1, then we say the model is like really good. And when the model is like, for example, if value is R square is 0.95, then we say it like 95 percentage of the variability in the data is captured by the model. And when the R square value is 0, then we say the model is not a good model and it is just guessing whatever it is there. So that is the R square, which is a metric that tells us about the goodness of our fit or the model. And then, so initially, when we had the curve fitting example, we had linear fit, quadratic fit, and cubic fit. And we saw that compared to quadratic and linear fit, cubic fit was good. Uh, but then, uh, does that always mean that? So, if you have a fit, or if you have a function with so many parameters, will it always give a good fit? So, so if you have a function with so many parameters, a complex model, will it always give a good fit? So the answer is no, and this leads us to the concept of bias, variance, trade-off. So this is the bias variance trade-off. Suppose if we have a data that is generated from, I think this is given in the this in the lecture video. So as sir explains in the video, there is degree 0 polynomial and a degree 9 polynomial. So degree 0 polynomial is just a horizontal line which is a constant, and a degree 9 polynomial has many parameters. And uh, if you see under fitting, and overfitting, so you can, so the function with many parameters means degree 9 polynomial, and a function with uh, a very less minimum number of parameters is an example with the degree 0 polynomial. So just a line, constant line. Uh, so when you have a degree 0 or a degree 1 polynomial, uh, it will be too simple to capture the complex input output relationship. So the fitted curve in that case will be very far from the data point, both in the case of training and at the time of testing. So this is called as underfitting. When the model is too simple to capture the patterns in the data, then we say it is underfitting. And we say that the model has high bias. So when the model is underfitting, we say it has high bias because it lacks uh, the ability to represent this complex input-output relationship. So no matter how much ever data we give to I mean no matter how much data we add to the training data, uh, as far as we use a simple degree 0 polynomial, a constant function, to represent the input output relationship, it will always behave very poorly. So then the model is said to be underfitting. And overfitting is, so when you use a degree 9 polynomial which has so many parameters, and then you see that the model will perform really good in the training set. The model will perform really good in the training set, but when we look at the testing set, it will behave very poorly. The error in the testing set will be very high, but in the training set it will be very low because the model has memorized whatever was there in the training data rather than the relation between the input and the output. Sorry, 1 second. I'll rejoin. So the model has learned the pattern rather than understanding the relation between the input and the output. So then we say that the model has, the model is said to be overfitting and it has high variance. So a low bias would mean that the model fits the data perfectly, and high variance would mean that the predictions change drastically with small changes in the training data. That means it has learned all the noise in the data. So, this is what underfitting and the overfitting means. So, this is so error in the model would be a sum of so the expected prediction error on the new data. It can be mathematically like represented into a sum of three different components. First one is the bias squared, then variance and noise. So this noise is some inherent randomness in the data, which no model can do anything about. And bias is how far is the average prediction from the true answer, and variance is the sensitivity of the model to fluctuations in the training data. How far is the average predictions from the true answer, and variance is the sensitivity of the model to fluctuations in the training data. So here as we use a complex model, so underfitting is when we have high bias. As we increase the model complexity, the bias will reduce. The model can represent more complex function, but then another issue is the variance will increase because the it tends to learn all the noise. So the optimal model that we want should be having a good balance of bias and variance. So, so then we'll do some question. So an R square value of 0.90 means 10% of the variance is explained by the model, 90% of the variance is explained by the model. So given SSE is 238.5 and SST is 1022.75, what is R square? So R square is 1 minus SSE by SST. So just have to substitute these values. You will get around 0.77. So there is a data point minus 0.5 and 48. And you are given a function that is, it is 0.77. Model T hat is given by 99.57 plus 79.28x. So what is the prediction? At x is equal to minus 0.5. Yeah, so we just have to substitute so this is the model or the function. So 99.57 plus 79.28 into minus 0.5. So it will be 9 minus get around 59.9. Yeah, 59.93. The expected error decomposes as bias plus variance, bias into variance into noise, bias square plus variance plus noise, bias square minus variance. Yes, it is bias square plus variance plus noise. As the model complexity increases, so when model complexity increases, the bias will decrease and the variance will increase. If the training error is low and validation error is high, the problem is, so then it is overfitting. So we know about this bias variance trade-off. Um, so when it comes to practice, we will not have access to many different data set. I mean, will not have access to large number of data set to check whether your model is performing well or not. So you split your uh, data into three main parts. One is the training set, another is validation set, and then a test set. Um, so we train the model on the training set. So like this, uh, so we started with the function f of x, and this function had certain set of parameters. And these parameters, these are learned through training on a specific set of subset of. So you have a sample with 1,000 rows of data. I mean, you have a data set with 1,000 samples, and from that you take 800 rows or 800 sample, and then from that you find this f of x with the optimal w1, w2, etc. That data set is called as the training data set. And so another thing is the validation set, another subset of the whole data set. This is where you monitor how your model is performing, and then there is a test set where you finally evaluate on how your model is performing. So this is just a broad classification of training, validation, and test set. There are many different evaluation strategies as you like come across the future videos. You will learn about cross validation, K4 cross validation, leave one subject out cross validation. So there are many such strategies that we use to evaluate the model. Uh, so this is one way. This is the general way that we tell there is a train set, there is a validation set, and there is a test set. So in the model, I mean, before we learned about overfitting. So overfitting is when the model have more complexity. We have a complex model. So for controlling overfitting or the model complexity, one technique is this technique called as regularization. So the key idea here is that you add a penalty term to the cost function. So that the weights do not become too large. So large weights sometimes they are like a symptom of overfitting because they allow the model to make extreme prediction in response to small changes in the input. And in the video, Sir tells about L1 and L2 regularization. So in L2 regularization, you add the squared magnitude of all the weights to the cost function. And in L1 regularization, you add the sum of the absolute values of weights. So here you add the squares and here you add the absolute values of the weights. So we'll check uh, some questions based on this. So regularization works by increasing the model complexity, penalizing large weights, adding more parameters, increasing the learning rate. So it works by penalizing the large weights. L2 regularization or ridge regression, it adds which term to the cost function. Yeah, so it will add the square of the weights, sum of squares of weight. Yeah, so it will add the absolute uh, value sum. So when we were learning about gradient descent, so for gradient update, we have taken all the n samples or all the samples in the data set. Uh, so this is one way to do it, where you take a set of samples uh, and then update all the weights uh, based on that gradient that you calculated from the n samples. So that is called as a batch gradient descent, where you take a batch of examples, batch of data, and then from the batch you calculate the gradient and update the weight. Now another example is the stochastic gradient descent. So instead of taking gradient over n number of samples, we take only one random sample at a time. So one random sample is taken at a time, and the gradient is computed on this single sample only, and the weight is updated. So it is one issue is that since the weight is updated at every time point for every sample, the the cost function, if you see the cost function, it will be very oscillating. Like the cost function will be very oscillating. It will be very noisy. So the middle ground in between this batch gradient and stochastic gradient is the mini batch gradient descent. So you split that training data into small batches of say 32 or 64 or any other number of samples, and then you compute the gradient and update the weights. So this will be much faster than the full batch gradient descent and also less noisy than the stochastic gradient descent. So it's like a middle ground uh, in between these two. So there are some like variations of these gradient descent which are discussed in the video. So one is the standard gradient descent update. It can be very slow to converge, especially when we have like a flat region. So one simple and effective improvement is the momentum. So it's like if you have a hill and imagine there is there's a hill and there's a ball that is going down the hill. So the velocity, if you take its velocity, it does not suddenly reverse the direction at every time step. It accumulates the speed in the direction in which it is rolling. So the momentum adds this concept to the standard gradient descent to make it converge faster. So instead of updating the weights directly by the gradient, there will be also something called as a velocity vector. And this velocity vector is computed as a combination of, it's a weighted combination of previous velocity vector and the current gradient. So we start with some random values and then this is updated based on previous velocity vector and current gradient. The details of this is the formula and all is given in the video. So the good thing with momentum is that it will accelerate the convergence. So it will help converge the standard gradient descent fast. And then another variation that is mentioned in the lecture video is the Nesterov accelerated gradient. So here, instead of evaluating the gradient at every position, um, they look at, so they take the momentum to get, so they look ahead and then evaluate the gradient there. So this will tell you whether the whether you are going correctly before you overshoot. So so this change, like you look at the gradient at the look ahead and gradient at the current position. So that will give, compared to a standard momentum, it will give better convergence. That is the main idea. So it incorporates information from the future gradient. So it looks ahead and see what is there before before taking that step, and then it updates the weight. So this weight update rule is also given in the example, I mean in the video. Then there is ADAGRAD. So this is the adaptive learning rate. So whatever method that we have discussed so far, that has the same learning rate alpha for all the parameters, but uh, some parameters, if you see, they need to be changed fast, and some parameters they might need to be changed slowly. So ADAGRAD makes use of, like, it has this adaptive learning rate per parameter based on the history of the gradients. So, based on the history of gradients, it will have a separate learning rate for each of the parameter. But then it is not like very much used. One disadvantage is the like as the sum keeps some of the squared gradients, as it keeps accumulating, it will never decrease. So another one that was discussed in the video is this RMS prop, and this was introduced to fix the Adagrad's vanishing learning rate problem. So vanishing learning rate means in the uh, as like as we go, then the learning rate seems to go to a very lower value. So eventually becoming zero, and then there won't be any update that is taking place. So that is fixed in the RMS prop. And another thing is the ADA delta. But so this is somewhat similar to RMS prop, but it has a exponentially decaying average of the squared parameter updates. So again, for this one, the update rule is given in the video. Uh, One popular optimizer that is very commonly used in modern deep learning algorithm is ADAM, which combines the ideas of momentum and also RMS prop. Um, so we don't really know, will not know initially what optimizer is good for our data. So we keep on trying different optimizers, and finally, uh, like there will be one that can optimally fit our data. So I didn't add the the update rules so that I can ask in the question. A mini batch size of 1 is equivalent to batch gradient descent, stochastic gradient descent, full batch gradient descent, diagram. Yeah, so it is stochastic gradient descent. Yeah, so it is the inherent randomness. So it predicts the future training data. It evaluates the gradient at the look ahead position. It uses second order derivative. It runs multiple iterations. Yeah, so it will evaluate the gradient at the look ahead position after the momentum step. Uh, if you have missed the assignment, I don't think there will be a chance to attempt it again. I mean, the same assignment. So if it is for week 4, if you have missed week 4, I think the date is already over. You won't be able to do it. But then I think missing one is fine. Uh, they will take around this much percentage for passing. I don't remember the exact percentage, but you can see it in the discussion, not in discussion forum. So there is an announcement section. If you go to the announcement section at the bottom, you can see the percentage that is required. a key advantage of stochastic gradient descent over batch gradient descent. Yeah, so it enables online learning because it processes one sample only at a time. Yeah, so this gradient at the look ahead position. Which optimizer combines momentum and RMS drop. Yeah, so this Adam. If train error is 2% and validation error is 20%, then it is overfitting. No, so Adam and RMS are not same. Adam uses the concepts from RMS and ADA delta. So they are not the same. Yeah, so if a degree 11 polynomial fit the training data, but validation error is very high, then we should apply regularization or we should reduce the polynomial complexity. Which of the following is a hyperparameter? The weight, learning rate, weight, and predictions. Yeah. So, it is the learning rate. The others are learned during the training. One question that is generally discussed. So, thank you all for attending.